Hello folks, today I want to talk about system design for a web crawler. Now before I get started, I want to mention that this particular design which I'll be walking through is heavily inspired by this particular article by Hello Interview. So a lot of what I have learned is through web crawler. A lot of what I have learned about web crawlers through this particular design, and that's what I would be reproducing today. Cool. So before we start, let's talk about the sorry. Let's talk about the requirements for this particular design. So let's start with functional requirements. Now the first functional requirement is that given a set of seed URLs, we should be able to crawl the URLs. Second would be extract the linked web URLs in the web pages and crawl those URLs. Third is the 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 crawled data should be available for later use or reference. Cool. So these are our functional requirements. Now moving on to non-functional requirements. So the first is scale. So let's assume that we have to crawl a lot of websites. Let's say somewhere around of 10 billion URLs. Second is fault tolerance. That is, don't miss out, not miss out, don't lose progress if a machine goes down. Third would be efficiency. Let's say need to crawl the URLs in 5 days. So we have scale, we have fault tolerance, we have efficiency. Durability is given, that the data should be durable, it should be stored. Okay, that's it. I will add something else if something comes to my mind. Now let's talk about out of scope. So the first thing is support for websites with dynamic content. So let's say JS rendered web pages. These kind of web pages require a headless browser like Puppeteer to crawl. Second would be support for websites which have, let's say, login functionality. What else? Cool. Let's now talk about the system interface of the system. The first is input, which is set of seed URLs, and output would be crawled data. And then let's also talk about the data flow of this particular system. So crawler will pick URLs from frontier queue, which is your seed URLs. After that, once it has picked up the crawler, it will hit the DNS to get the IP of the URL. After it has the IP, it will hit the machine itself. So hit the machine or the web page server and retrieve the HTML data. After this, we need to parse the data. Parse the HTML data, extract your text data and store both the data uh, in blob storage. So okay, fifth would be extract the linked HTMLs in the web page, and then sixth would be repeat steps 1 to 6, 1 to 5. Cool. So until the queue is exhausted. So yeah, I think this is it. If anything else, if I remember anything else during, yeah. So yes, now I remembered. So the fourth was politeness. So what this means is that we should be able to adhere to the requirements of the website. Every website has, not every, but a lot of websites have a file by the name robots.txt, which helps us understand at what rate can we crawl that particular website. So that is point number one of politeness. And second, we also do not want the machine to go down. We should not be overwhelming the machine, the servers, by n number of by a lot of web crawl requests. So these two things should be taken care of. So respect robots.txt, and the other one was rate limit the crawl. So industry standard is 1 second, that we should be crawling any particular website for not more than once per second. So yeah, these are the functional, non-functional requirements and a couple of out of scope items. We have defined system interface and data flow, and now we can get started. So let's start with the most basic functional requirements first, and let's satisfy them first. So what we have is a frontier queue, which is your seed URL, which contains your seed URLs. And after that we have, let's say, our crawler. So crawler hits this frontier queue, it gets a seed URL, and then it hits a DNS. After hitting the DNS, it has the IP address. So this will be a two-way communication. Yeah. And after it has the IP address, it will then hit the web page. So again we have this. This will not be this will not be a two-way communication. So now, so the crawler has done a couple of things. One, it retrieves the seed URL, then it hit the DNS and retrieve IP, then it crawls the web page, and then one more thing it does is it also parses the web page. Now after doing all these things, what this particular machine will do is write this data to S3. So we have an S3. So this is a blob storage. We are using S3 for this, assuming we are in an AWS environment. Okay. So now it writes the data, both the HTML data as well as both the raw data as well as the parsed data to S3. And after, it also does one more thing. It extracts the URLs from the web page and then puts them back in the frontier queue. So this is the final step, so as to speak. Extracted URLs. Now this is the most basic system diagram for this, and it satisfies our it satisfies the functional requirement. So given a set of seed URLs, we should be able to crawl the URL done, extract linked web URLs in the web pages and all those URLs done, and crawler should be available for later use in reference. So okay, so this is done. Now we can get to our non-functional requirements. So let's talk about fault tolerance first. So there are a couple of things in fault tolerance, and the first thing is this particular thing, this crawler is doing a lot of work. It is doing at least 4 to 5 different tasks, and this is not a good state. This proves to be a single point of failure. So what we want to do is we want to reduce the number of responsibilities this particular machine is taking care of. So let's do that first. So after crawler, we also have, let's say, a parser. So we have a parser machine, and it does a couple of things. It parses the web page. It extracts the URLs, embedded URLs, and put them in queue, and store parsed data in S3. Okay, so we have a parser. Now a couple of things here. One, how will this parser know that a particular URL has to be parsed, has been crawled and it has to be parsed? So for that we will have one more queue here, which is your parser queue. And this is from where our parser will get the URLs. This would be populated by your crawler. So we have a link here, and obviously this connection will go away. We need to connect these two sources. Okay, and then we need one more thing here, which is your state management for the crawled URLs. So we should have a database here which takes care of the metadata for the URLs. Now it is possible that we do not have that, in the sense that we crawl a particular URL and we share the S3 link of that particular URL, of that particular raw data into this parser queue. So there would be, so the key would be the URL, and the value would be the link to the S3 location. But it will not help us to, let's say, after after the crawling has completed, we want to see what are the different URLs which we crawled. These URLs would be more than the URLs which were given to us in the frontier queue. So to have that kind of information, it is better to have a database which keeps track of the URLs. So this is your URL metadata, and this could be Dynamo database here. No SQL will work, but SQL will also work. That's not a problem. So the fields are, so we have a URL, we have an ID, we have URL, and then we have S3 link to URL, which would be added here. The other question which can occur is, why can't we just share this particular payload in the payload to this parser queue? Why can't we share the HTML raw file itself? The reason is that it's not recommended. The file size might be more than the expected payload here. So it's better to have either a link to this particular row entry from which will then which will help our parser to query this database and get the S3 link, and then put retrieve and then put it back. So we have a connection here. So after the crawl, let me draw the lines, and let me draw the connection, and I will just tie this up. So upload raw, that is HTML file, and then this will upload parsed, that is text file. So the flow looks like this. We will get a we'll get a URL from the Frontier queue. The crawler will get the URL from the Frontier queue. It will retrieve the IP address from the DNS. Then it will hit the web page. It will get the raw data. It will crawl the raw data. Sorry, it will crawl the website and it will upload the raw HTML file to S3. Once that is done, it will make an entry in the URL metadata database with at least these three values. Then there could be some other metadata as well, which we are not adding right now. And once that is done, then it will create an entry into your parser queue. Now your parser will retrieve data from will read the message from this parser queue. It has a key value pair that this particular URL has to be passed. It will retrieve the S3 link of the URL from the metadata. It will download the file. It will parse. It will upload the parsed text to S3. And then whatever URL was extracted from that raw HTML, it will push back to the Frontier queue. Okay, so this works. This is the first thing on the fault tolerance part. But this is at our system level. The next question is, what happens if that particular URL or that domain is down for a while? It could be for any reason, in the sense that let's say that the server was not responding, or there was a network network breakage between our machine and the web page itself. There are a couple of ways to do this. One is to have a timer in the crawler machine itself, that let's say a particular URL failed. We will have that timer, let's say in memory of 5 seconds, 10 seconds, 20 seconds, whatever, after which we will retry. The problem is that what happens if that particular system, this node fails while waiting? We have lost all the information about that URL. So that means that we have to go back to we should be able to persist that information somehow in this queue itself. Now there are two queues which could be used. One is Apache Kafka, Frontier queue alternatives solutions. We'll explore two. One is Apache Kafka and second is AWS SQS. So Apache Kafka in this respect does not have a built-in retry mechanism, a timer mechanism. So we will have to have some kind of exponential logic inside our machine itself, inside our crawler. What that means is, whenever a particular URL crawl fails, we will have to have a logic inside a crawler which will keep track of one thing, is that which iteration was it, in the sense that am I retrying it for the first time, second time, third time, fourth time, whatever, and after each iteration it has to increase the duration of wait. So that logic has to be specified in our crawler itself. SQS, however, supports exponential retry out of the box. Now what that means is that let's say my retry my first try failed. So it will take back the message with a timeout of, let's say, 5 seconds. And if it after 5 seconds we pull back the URL, it fails again, then we can configure the timeout, the retry timeout, to be, let's say, 15 seconds or 20 seconds. So in that way we can exponentially ensure that in that way SQS does a lot of work for us. So that's the first thing. The second thing is, what if that particular website is down completely? It doesn't come online again. That seed URL might be broken, or the embedded URL which we extracted from wherever was dead. So in this case, we do not want to try exponentially. So again, we need to have a maximum try counter, which helps us to stop trying after X number of tries. Now again, Apache Kafka does not give this kind of solution out of the box. We'll have to implement it through some logic. SQS, however, gives this kind of functionality out of the box. So I do not know, I don't remember the exact the property, the configuration, but it allows us to stop retrying after a point in time, and then it moves this kind of messages to another queue, which is dead letter queue. So after if some particular messages have failed, they could be retrieved back from the DL queue, dead letter queue, to check why those things failed. So because of these added advantages, we will go for Amazon SQS instead of Apache Kafka. So let me just write here, this is our SQS, and because you are using SQS here, it makes sense to use SQS in parser queue as well. So yeah, so that was the second thing about fault tolerance. Now what else can happen? If the node goes down, we will automatically spin up another node, and at maximum what will happen is that that particular URL would have to be recrawled. Now the other important caveat here is that what if a particular URL was being read, sorry, a particular message was read from the frontier queue, our machine was crawling it, and then it stopped for whatever reason, it failed. So the question is, will that particular message be lost? Will that URL be lost? So the answer for that is no. Amazon SQS as well as Apache Kafka both have this particular way where we do not delete those messages automatically. We can configure them. The retention time could be configured. In SQS, we have to explicitly delete a message after our crawler completes the work. So that is one thing. In Apache SQS, the way it functions is that the consumer, which your crawler is in this case, keeps a track of some kind of pointer, some kind of offset at which message was read. So we can configure that as well to make sure that if any node dies down in between crawling, we do not lose that particular URL. However, as you're using Amazon SQS, this problem can be taken care of itself. The message would be hidden for a while so that other crawlers, other parallel machines do not pick it up, but it will come back online. It will be visible again if that particular message is not deleted by a worker. That is the visibility timeout which Amazon SQS provides. So that was on the fault tolerant part, and that is it. So we do not lose progress if the machine goes down, as is taken care of. So this is done. Now let's move on to let's say politeness. Now politeness comprises of two parts, as I mentioned earlier. Let me write it there only. So the first thing is respect robots.txt file. So this file is something like this, like you will have user agent, which user agents can crawl it. Then there will be something like a crawl delay, which let's say is 10 seconds. And the third is restricted, let's say which directories should not be crawled. So that is point number one. The other thing I want to specify is that this robots.txt is suggested by crawlers like Googlebot, but every website doesn't necessarily have. So there are cases, there are situations where you will not find this robot.txt in the root folder of the server of a website. So that is to be noted. So the other part of politeness is don't inundate the website server with a lot of requests. So the industry standard here is crawl every second, one request per second. So that means is that if let's say a particular website has 100 pages, we should not crawl it in less than 100 seconds. We should wait for every request, for every web page. We should wait between any two web pages. We should wait for 1 second. So these are the things about politeness. Now the question is, what about this robots.txt file? So what we can do is we can have another table here in the URL metadata, which is around, let's say, domain, and this contains all these three things. So it has restricted, it has crawl delay. Okay, so these details are in your metadata. Now what happens is, whenever a crawler retrieves a particular URL from the frontier queue, if it is the first time that domain is being crawled, we will retrieve the domain, this particular robots.txt, and will store those information in the domain table. After during every subsequent crawl, we need to check if that particular crawl delay if a particular page has been restricted or not. If it is, then we will just mark that particular page as skipped, and then we will move to the next thing. On the crawl delay thing, we need to have some kind of state. So let's say that we have in memory URL state. This can be Redis distributed thing, which whenever we are going to query a particular domain, we check what was the, so this will have two things. It will have a URL and it will have last crawled. So by the way, this particular information could be in this particular table as well. So but for faster access, I am using a Redis machine here, and also it will come in handy as the design goes by. So we have a Redis thing here, which we query every time when we are going to crawl a particular web page. We check when it was last crawled, and we can have, let's say, a TTL of the TTL would not be helpful here. So let's not have a TTL. We will have, let's say, we can just have a copy of crawl delay here. Okay, so these two could be kept in sync. Anyway, so the politeness from this part is taken care of. Now the other part is the rate limiting thing. So for rate limiting, the Redis in memory comes in handy. We can check whenever that particular machine, whenever that particular web page was crawled, and if it was more than 1 second, in cases where the difference between this crawl delay and that 1 second, if the crawl delay is higher than 1 second, of course you'll have to wait for this crawl delay. But if it is less than 1 second, then we can check if the particular machine, if the particular website was crawled. If it was not, then we will put that message back in the SQS, and we will crawl it next time. The problem here is what happens if multiple machines try to crawl that particular web page at the same time. So let's say different URLs belonging to that same domain are available back to back in the SQS, and our different crawlers, let's say 5 crawlers, pick up 5 such nodes, 5 such messages, and then they try to hit the URL simultaneously. Now this is kind of a race around condition where only one request will pass and the four will fail. Then and then this situation can go on endlessly. If let's say if the number of URLs are 100, so every time will this loop will go. So the way to get around this is to add a jitter, a small lag which is coming from a random value. Now that jitter will make sure that this kind of condition doesn't arise. So okay, politeness is also taken care of. We are expecting the robots.txt and we are also rate limiting the crawls. This is fine. Now let's talk about the scale and efficiency. Now it is a good idea to assume what are the number of what is the size of each web page, and in the particular example, in the particular article I showed you was somewhere around 10 to 2 MB. Let's just go with that. So if you are talking about calculations, we have 10 billion pages, which is 10 to power 9. We have 2 MB of web page. So the AWS instance, which is a memory optimized, sorry, input output IO optimized machine, which the article talks about, is let's say 400 Gbps. This is bits per second. 400 Gbps. It supports 400 Gbps transaction limit. So that means we would be able to crawl 10 billion pages of 2 MB each in how many seconds? So the question is, so we have 400 into 10 to power 9. This is divided by, first of all, 8 bits per second. 8 bits, so this is now 1 byte, and then this is multiplied by 2 into 10 to power 6. Okay, so this will come around, and we also need to look into, so 400 Gbps, this will be give us number of seconds. Okay, so this is 10 to power 3. Okay, so this will come, let me just check once. 400 divided by 16 equals 25. Yeah, so this will come around 25k. So we are 25k per second pages are being crawled, and the number of web pages are 10 billion. So 10 to power 9 divided by 25 into 10 to power 6, 10 to power 3, sorry, my bad. So this will be around 10 to power 6, and this will be let's also add 10 to power 6. So this 10 to power 6 is the number of seconds in a day. Okay, 10 to power 5. Sorry, 10 to power 5. So this is 100 by 25 equals to 4 days. Okay, so one such machine will be able to crawl the 25k pages in 4 days. The problem here is that this is highly optimistic. We are not talking about any delays. Now, assuming that this particular machine is 30% functioning, the success rate is around 30%. So that means that we will need how many machines to come. So this will take around 12 days, right? 4. Yes, it will take around 12 days. Efficiency. So this means if we want to sorry, it will take around 13 days, 13 to 14 days. Now if we want to crawl in 5 days, we can have around 3 machines will crawl in around 5 days, in less than in 4 to 5 days. Cool. So these are the calculations. This is the number of machines we need. The problem, the next question is of efficiency. Are we efficient enough? So we have taken care of a couple of situations here. We have the fault tolerance part. We have taken care of that any no data should be lost during this particular thing, during this crawl. Whatever cases we could have covered, we have covered them. So the one thing which Yuan talks about in that article is about hashing, so that we do not crawl an already crawled page. But I did not understand that part, because hashing a particular web page doesn't stop us from crawling, so that crawl is already happening. With respect to this particular thing, the parser, this will scale horizontally. So we do not need to have a defined number of crawlers to begin with. We do not have that bottleneck. Crawler is the bottleneck here. So at a point in time, if there are a lot of items in the parser queue, we can scale the number of crawlers to scale the number of parsers to maybe 50, 100, whatever, depending upon the number of queues, number of items in the queue. So okay, so that is taken care of. Scale is done. The other thing in efficiency was about DNS. So if we are hitting it again and again and again, the problem could be that the DNS could be a bottleneck, and there are a couple of ways to handle this. One, we can have a cache in between, which caches the URLs, the IP addresses. That is one. We can also Redis cache, yeah, for IP, URL, IP mapping, yeah. So this is one thing we can do. The other thing we can do is we can just increase the number of DNSs. So instead of one, we can have multiple. So this will, to an extent, take care of this problem here as well. Okay, so we have covered a lot of items here, and this is our system design for a crawler. I hope I have not missed anything, but let me just check if anything has been missed. So okay, security, so this was not there, and this was not there, and this was not there. Okay, that's fine. These are out of scope requirements. So we have here data flow is there. Okay, this is fine. Potential deep dives, fault tolerance, null fetcher, text extraction. Okay, this looks as hot. I did not add these things. I will try to remember to add these later. Okay, so we do that, or is fine. In memory, Kafka and exponential backoff. Okay, take it. This was manual. Then next we have, oh, I forgot to add a DLQ, but I verbally spoke about it, so that is fine. Then okay, then robots.txt, rate limiting. Okay, okay, so we have a domain table which I added. That's fine. Rate limiting, we added this rate limiter here, and then we talked about jitter as well. Scale 10 million pages, 2500 pages per second. Yeah, this is something I forgot. Okay, now 10 million pages is 15.4 days. Okay, 3.85 days. Okay, ठीक है. Parser, this is fine. DNS is done. Efficiency part. So this is the part which I did not understand. I have posed a question here, which I am not sure has been answered or not. Let's see. Who cares? Yeah, so I've asked this question. Let's see if they reply back. So yeah, that was, yeah, I forgot this one. Crawler traps. So we can have state a depth thing where we crawl the number of pages from that website only a number of times. We just read through this. Crawler traps pages are designed to keep crawlers on the site indefinitely. They can be created by having a page that links to itself many times. So by having a page that links to many other pages on the site, if you're not careful, we could end up. Solution is pretty straightforward. We can implement the maximum depth for our crawlers. We can add a depth field in the URL table. So they have added a depth field here. Okay. And metadata and increment in field each time follow link. Okay, that's cool. The data exceeds a certain threshold, we can stop crawling the pages. This will prevent us from getting stuck in the crawling trap. Okay, cool. So yeah, that was it for the crawler design, and yeah, thank you. Thanks a lot.